Okay, well, I'd like to finish up sections 4.1 and 4.2 in this video. So let's see, in the last video we talked about compound interest, right? There's the compound interest formula, and then there's continuous compound interest. And I had mentioned that, I don't really see banks that offer continuous compound interest. Like there's no magical bank out there that's going to give you money every second of the day forevermore, right? So, I gave an example where, like a better example of using this formula would be to study the population of the world. Okay, the population of the world is continuously growing, right? Continuous, that's an on-purpose word that I'm using there. And so it makes sense to have this formula be used for that example because I don't have a start-stop type thing going on there. Okay. Let's try this example. So the population of Texas was about 30 million people in 2022, and it's increasing by 1.6% each year. Estimate the population in 2032. Okay, so for this problem, I'm going to use the equation P of t equals P sub 0 times e to the RT. Now that equation looks very much like the PERT equation. This equation here, we're going to use this quite a bit at the end of this chapter, okay, when we look at population growth and decay models, okay? The reason why I'm using this formula here is because the population of Texas is continuously changing, right? And it's increasing by about 1.6% per year. So because it's continuously changing, continuously, that's an on-purpose word, like I want to use a formula that represents the PERT equation, okay? P sub 0, that's the initial size, so be 30 million people in 2022, and I'll just keep track that, my number is going to be in millions here when I do this, but so P sub 0 would be 30, we'll call it, times e to the power 0.016 is the R value, and then times t. Okay, so here's the formula that we're going to use in this problem. Now, I want us to estimate the population in 2032. Well, it's been 10 years since 2022. And so all I have to do is plug in 10 for t, and then I'll be done. Okay, so if we do that, we got 30 times e to the power 0.016 times 10. 0.016 times 10 would be 0.16. All I do is slide the decimal point to the right 1 unit. And 30 times e to the power of 0.16, if I type that into the calculator here, okay, so e to the power 0.16, I get that, and then times 30. And I'm getting 35.2, roughly, okay? Now, the number is in millions, right? There's not roughly 35.2 people in Texas, okay? So there's 35.2 million people in Texas. So that's what we would guess would be the number in 2032, okay? So, it would have grown by about 5.2 million people in that 10-year time span. Here's another example. So the amount of medication in the bloodstream of a patient is given by the equation A of t equals A sub 0 times e to the power negative RT. Okay, by the way, so I mentioned that this function represents how a population is either growing or getting smaller over time. We're going to do a lot with this particular function coming up, okay? So A of t, A is the amount. A sub 0 is the initial amount of concentration in milligrams per liter. R is the hourly percent decrease of the drug in the bloodstream. And T is the elapsed time in hours. Okay, now one thing to mention here, notice that the power is a negative. What that means is that over time, the population is going to get smaller. Okay, like if you inject a medication into you, over time, there's going to be less and less medication in the bloodstream, right? Okay, whenever the power is a positive, that means that the population is going to be getting bigger over time. Okay, so like in this problem here, like it makes sense that the power is, a positive number rather than a negative number because it's increasing. The population is increasing. Suppose also that A sub 0 is 2 and R is 0.2. Find the drug concentration after 4.5 hours. Okay, so A sub 0 is 2, so I inject 2 milligrams per liter of this stuff into the bloodstream. And R is 0.02. That's a negative power, though. Okay, because as time goes on, there's going to be less and less of this medication in the bloodstream. So we want to find out, how much is going to be there in 4.5 hours. Well, T is the time, so all I'm going to do is plug in 4.5 there for T and then simplify that. Okay, so let me do that. I have negative 2 negative 0.2. Negative 0.2 times 4.5 is negative 0.9. Okay, so then I type in 2 times e to the power negative 0.9. And, okay, so e to the power negative 0.9. And I get that. And then times 2 means I get that. Okay, so I'm getting roughly about 0.81 milligrams per liter of this stuff is left after 4.5 hours. So initially, I have 2 milligrams per liter, and after 4.5 hours have gone by, now I'm only down to 0.81 milligrams per liter. And as time goes on, there's going to be less and less in the bloodstream. Okay? So, these are some examples of exponential functions, right? And we're going to do, more with this stuff later on in the chapter. I'd like you to look at the homework in section 4.1. It's on page 281, and then 4.2, it's on page 294. Okay, so in the next section, I'm going to begin logarithmic functions there. Okay.